simplest to understand is imagine average intensity, right? If I just take the average intensity over a circle, that function doesn't care how big the circle is. It's just going to compute that function over whatever size circle you give it. And in fact, if it were a constant gray value, if you kept making the circle bigger and bigger and bigger, it wouldn't matter. The function would stay the same. If you have a function that changes over different corresponding regions, then that function would go up and down as you looked over those different regions. And if I zoomed out of that thing, it would go up and down again, but now it would go up and down faster because as I grew my circle, I would be covering more of that picture as I moved that circle out. Now, I know that was clear as mud, so let's take a look at a picture, all right? So imagine at a point, you compute one of these scale invariant functions, like average intensity, over a range of neighborhood sizes, okay? So we're at a single point, and we're computing this function f over different region sizes. And you'll notice that, well, it goes down, and then it goes up, and then it goes down again. So that's my function that I've computed over different region sizes, all right? Now, let's suppose in my next picture, I shrink the thing down by half. Well, now, as I compute that same function over the same region sizes, 2, 4, 8, 16, right, it's going to take the same shape, but it's going to get there faster, which is why this function is essentially just a squashed version of the one on the left. But it's the same function, just squashed. Well, what that means is, suppose we pick the maximum of that function. I'm going to call that S1 in image 1 on the left. And I take the same function, and I'm at some other point. I'm same function on point in the second image. If I were to take the maximum there, it would be a different size, right? Because that image had been squished in half. That would be S2. But these two neighborhood sizes would be covering the same region of the image between the two pictures. So they would be matching scales. So the important thing is, I do each one of these things independently. That is, I do this thing, and at this particular point, I find my maximum function, my maximum of the function. I say, that's the natural scale size that I'm going to use. Then I come over here, and I go to my other image, and I do over here, and I'm at some interest point. Remember, we found our interest points, and I look over all these different region sizes, and I say, aha, this is the scale there, and I compute that function, and magically, these two scales correspond. These are the same chunk of image. Here's a very nice illustration of that. Here's a picture of probably some beautiful church on the inside. Here it's just white and gray in some church in some mountainous area of Europe, I'm going to guess. And you'll notice that there's a function here that we're computing as a function of scale, and here it is. And this is the maximum point. And this circle is meant to reflect the scale size of that maximum. Here we have that same image zoomed way out, computing at this interest point. So we've got the same interest points. You notice that this interest point is just sitting at the top of this little chimney thing here. We compute the function again, and again we take the maximum, and that's going to be this circle. And the really cool thing is that this circle and this circle are the same components of the image. Those are the two scales to operate at. If we want to find descriptors that match, that's coming later. Basically, the scale of my detectors in one image should be big, and in the other image should be small. Also, the scale of my descriptors and my detectors. So I told you before that nobody actually uses average intensity. Right? So what will we use? Well, let's think a little bit about what it means to be a good function for scale detection. All right? Basically, what you want is you want to be able to find these maxima as a function of the region size. Okay, so it would be bad if for large variation of the region size, basically the function stayed flat. That would be bad. Another thing would be something that wiggled too much. There's only 3 wiggles here. Imagine there were a lot of wiggles, because we'd like to find a maximum, and we'd like to find really just, one or a really key maximum that we can pull out. So, this becomes your ideal function. It's sort of a cartoon of the function there. So the functions that people use, what you want is one that, responds nicely to contrast. right? Because the idea is, you're going to have edges at some scale. Oh yeah, remember that? Right? So edges occur at some scale. And if you were operating at the right scale, you'd get this nice sharp contrast. And if you were, as you got away from it a little bit, it would fall, and if you got too far, it would fall down on the other side. So there's going to be something having to do with contrast, or finding points of high contrast. What are points of high contrast? Remember edges? Okay. So in fact, some of the detector operators that people used are just applying, remember kernels? And these are the kernels like when we applied differential operator kernels. We just apply a kernel to the image and use the output. Now, one that people sometimes use, and we actually talked about this Laplacian of Gaussian. When we talked about edge detection, we said, well, in the first derivative, there was two directions you could do. You could do an x and a y. And then we said, well, if you have to worry about the second derivative, there's all sorts of challenges. But we mentioned something called the Laplacian of Gaussian, the Mexican hat operator, right? And this was this one, and the equation is written here. I actually pulled out my own MATLAB here and made a little 3D plot of what it looks like. And here this shows you. It's an operator which essentially is a second derivative operator. And we talked about zero crossings. Go back and review the property of what we did on edge detection. You'll see it there. So that's the type of operator that you could use. Now, something that we didn't really talk about, instead of doing this whole Laplacian of Gaussian, which involves these sort of annoying second derivatives, there's a cute little trick you can do, and that's called a difference of Gaussians. And that's what's written here, is basically if you take one Gaussian and you subtract from it another Gaussian with a slightly different, or some factor different sigma, you get a curve. And what's plotted here in the red is the difference of Gaussian, and in the blue is the actual Laplacian. And you see that the values are almost the same. So for doing the work here, it's a lot easier, since you're computing these Gaussians anyway, to just subtract these. One of the things also is that these Gaussian, the difference of Gaussian and Laplacian is circularly symmetric, so it's totally invariant with respect to orientation. Okay, so as you rotate your image, nothing changes. And it says that it's invariant to scale. What that means is it's just like it's a scale invariant function before. If I blow up the function and then I make my operator that much bigger, I'll get back the same value that I had before. The way we do that for what's called key point localization, and key point and interest points are used similarly. Key point was the term used by David Low in SIFT. We'll talk about that in a minute. Here is the general idea. We want to find robust extremas. So maximums. By the way, you can also find minima. So if you remember for the Laplacian, it goes through zero, goes positive, negative. So if you took the absolute value of that, say, the square, the value that's zero is a good point. Anyway, you want to find robust maximum minima in both space and scale. So that's what's drawn here. We haven't talked a lot about scale space, but the idea is, I have an image, and then I could filter that image again, and I could filter it some more, and you can think of it as a coarser and coarser scale. And I have some point, and you can think of that point as having neighbors to the left and right, and you can also think of that point as having neighbors up and down in scale, and that's referred to as scale space. A specific way of using that scale space was suggested by David Low in the SIFT paper. But at that point, there was a specific suggestion of do this difference of Gaussian pyramid. What I mean by that is you do it at different scales and over space to find maximum values in all of those. Now, sometimes you might land along edges. Okay, so you're on a maximum value, but it's really just the maximum along an edge. So what you have to do is you have to eliminate the edge points. In fact, if you recall, we first introduced Laplacians of Gaussians to find edge points, right? Even though it was a circularly symmetric operator, you were able to find these edges. So from way back, from the Harris, we said, well, edges aren't so good for finding specific locations. We want it to be more like a corner. So basically what you would want to do is you would want to find points that have these extreme values, then make sure that, thresholded, that they were extreme enough, if you will, and then make sure they're not edges. So here was a particular method by which it was done, and I show you this so you can take a look at the results in a minute. Basically, what was done was you take your image and you deal with it an octave at a time, and an octave is a doubling. So what you do is you make it blurrier and blurrier and blurrier and blurrier. Then you take half, then you reduce that down to half the size and make it blurrier and blurrier and blurrier and blurrier. And what you do is you subtract these off to get your difference of Gaussian images. Then within each one of these Gaussian images, you're going to compare a pixel. And in fact, if I go back to this picture here, I'm going to compare this pixel to each of its 8 neighbors, and each in the same plane, and there are 9 neighbors above it and 9 neighbors below it. And if you're a maximum of that, you're going to say, aha, I'm an extrema. So here you have a picture of Einstein, and each one of these is a different octave. It's cut in half, cut in half, cut in half. And then you can see we go from crisp to blurrier to blurry to blurry. It's probably the only time Einstein was fuzzy in his life. And then, just as we showed in this picture before, we can subtract, example, these two and get that difference, all right? Or we can subtract these two and get that difference, right? So these are our difference of Gaussian images. And then what we can do is we can take each pixel in one of these and compare it to its neighbors in space and its neighbors in scale. And when you do all of that, you can find the extrema, and it looks like that. So this is an Einstein picture with really bad dots, but some of those extrema might be higher than their neighbors, but not very high. This happens in Colorado. So you want to make sure that the contrast or that value is higher than a particular amount. So we say, aha, here are places with contrast. But we say, wait a minute. We said before that when we use Laplacian and Gaussians, we might have nice contrast, but it might be high just in one direction, so along an edge. So what do? We remove the edges, and voila, these are our detectors, okay? And what's important here is these are detectors that are robust with respect to scale, because we pulled out all the extrema at all the different scales. And this was David Sift detector. So this can be written sort of like this. So for scale invariant detectors for SIFT, here we've shown that you're going to do difference of Gaussians in space and difference of Gaussians. You're taking all these different Gaussians and comparing them in space and in scale, and you're picking the maxima. And here's a reference from, again, the journal Computer Vision, where he talks about this. There is another approach that's quite related. It uses both things that we just talked about. First, you essentially do the Harris corner detection at lots of different scales. And then you also take a look at the Laplacian in the scale direction, and you find points that are the maximum in space in the Harris measure, right? That's like that non-maximum suppression, and are maximum in space in scale in the Laplacian direction. And this is sometimes called the Harris-Laplace detector. The paper here, ICCV, is one that's referenced. And, you know, I can show you, here's a nice little demonstration that with change of scale, that, well, first you can see the original Harris detector, in fact, does really poorly. That's what we saw before. The SIFT detector, that's the thing in the green line, that was the thing we showed you before, it does way better than the Harris detector, but along comes Harris-Laplace, and it does even better. And so you might say, well, of course we should use Harris-Laplace. I will tell you a lot of people do. I will also tell you that this graph comes from the people who invented Harris-Laplace. So, you know, your mileage may vary. What we've learned about today is how to deal with images that have large-scale differences between them. Frankly, if you have two images that are translated, rotated, made brighter, darker, etc., stretched a little, skewed a little, the scale may not matter as much. But if you had a large scale difference, then what you do is you try to find the same scale around the interest points by that scale invariant function, and you search for these maxima. All right. So where are we? So we know how to detect interest points. Here's a whole bunch of them. The next question is how to match them. So I've got points in my left and points in my right. How do I find the match? To do that, I need what's called a descriptor. I need to describe each of those points by looking at the little region around it and look for that in the next image. And that's what we're going to do next lesson. Welcome back to Computer Vision. Today we're going to continue talking about features or interest points, interest point operators, key points. In particular, Last time we talked, in fact, last couple times, we've talked a lot about how to find interest points, how to detect them. And we talked about the Harris operator and other kinds of ways of finding them. And here, for example, typical picture of finding interest points in